Debugging with GDB often means running in noise. When tracing functions like do and map, we were forced to pause on every call, even though we may only care about invocation from a specific caller like load ELF binary. Standard breakpoint lack context awareness. They stop execution by not understanding. That's why I built CGDB, a GDB plugin that filters breakpoint by code chain provenance, stop only when it truly matters. What are the limitations of GDB? Standard GDB force a mandatory pause every time a breakpoint is hit. However, we don't always need such high frequency interruption. For instance, we might only want to inspect the parameter of do and map when it is triggered by load ELF binary, rather than every single time do and map is called. And next, so what is my approach? The core mechanism of CGDB is to identify the execution path between a sub breakpoint and its root caller by inspecting stack frame. Whenever the designated root is hit, CGDB capture and store the current RPP. Subsequently, when the execution reaches the sub breakpoint, CGDB perform a stack backtrace to traverse the frame. If a frame matches the previously stored RPP, it confirms that the sub breakpoint was indeed triggered by that specific root context. How is CGDB built? CGDB is implemented as a Python extension leveraging the GDB Python API. The core logic revolves around two custom data structures: breakpoint struct, which define the hierarchy, and callback struct, which manage the runtime state. When a root is triggered, we don't just pause, we cache its RPP in a global registry. For every sub breakpoint, CGDB performs a deep stack walk. It extracts the RPP of each frame and performs a lookup in our registry. This allows us to determine the provenance of a function call with high precision even in complex kernel level execution like load ELF binary. Okay, now I will show you how to use the vanilla GDB to debug, and you will know why it is not very good in this place. Let's start a virtual machine first, and attach to it break at ELF map. ELF map. Okay, continue, and we should run a binary program here. Binary program, like ls, and it will hit the breakpoint because ls will Linux will map the ls in RAM, and we can see the signs, the value of signs, the value of file pointer, the value of clock. But it is very manually, not very automatically, so it is not very good. Okay, now let's see how to use the CGDB to debug in the same place, the ELF. Okay, now let's start the CGDB first and continue, and enter ls. I will enter ls, clear ls, and you can see at here, but another place easier to see is this file. This, you can see the history of the input. ls clear ls, and you can see this is very many segments, and CGDB can make it very beautiful. So CGDB is good in this place. Okay, sometimes we may want to know how many times a function call. then we can use the CGDB, like this function. Alloc frozen page no proof. This is a function for alloc page, and this function have two paths to alloc the page. First is the fast path, and the second is slow path. And the Linux developer say the page will likely to alloc from the fast path and not likely to alloc from slow path. But what if that developer is very bad? Maybe he want to scam us and make the Linux bad again. Then we can use the CGDB to see it. Okay, let's start a virtual machine first. Okay. Okay, let's go to my test program. This test program will... never mind. You don't need to know what this program will do. It's a stress program. Continue. Here. Okay. Yes. Then you can see it always call the fast path. I will wait until the slow path call execute, and I will jump to it. Okay. Ooh, this slow path already call. Because now the memory is very stressed and very less, so the body system will call this slow path. But we can see the fast path still call more than the slow path. And yes, that Linux developer is right. He is good. He will make the Linux great again. Okay. Thank you.